The objective of this quick primer, is to introduce a new methodology to solve the equations of motion. Um, in the case of simple pendulum problem, we can simply directly get the equation of motion by taking the moments, by writing the moment balance equation about the pivot point. The objective of this video is not to derive the equation of motion of a simple pendulum problem, but to introduce the methodology to solve problems in multibody dynamics. Okay, and simple pendulum problem being the easiest one, we'll start with that. Okay, let us look at the problem statement. Let's say the torque acting on the body A is given, and the initial angular position and angular velocity are also given. So we are required to determine the angular position and angular velocity for a specified time span. So this is the problem statement. So we have two bodies here, body A and body N, and there is a torque acting on body A with respect to body N at the pivot point AN. Okay, AO is the center of mass of the body A. Okay, so we will be first defining the local coordinate systems as in the figure. So you have AO, AN and ANO as 4 points, and there are two bodies. Okay, and theta is the degree of freedom or the generalized coordinate. Okay, we have a local vector RAN, which is going from AO to AN as defined in the terminology video. So this is a local vector. Okay, so now the transformation matrix between the fixed coordinate system, ground fixed coordinate system N1, N2, N3, and A1, A2, A3, which is the coordinate system fixed to the body A, is as shown in the equations here, and the transformation matrix between N and A is given as N underscore A in that equation. So now we have capital RAN, which is the vector from AO to AN expressed in the ground fixed coordinate system. So okay, now next step is to do the position analysis, right? So there are 4 points, NO, NA, AN, AO. So NO, NA, AN are all 0, 0, 0. Position AO is minus RAN. Okay, minus RAN, which is, you can figure it out from the figure. Okay, so next is velocity analysis. We have the angular velocity 0, 0, theta A dot, omega A, and the velocities can be computed using the equations shown in the slide. Okay, so now we can also write the velocities as in this form, where, well, any velocity v is equal to j, the Jacobian j times theta A dot. Now these Jacobians can be determined by simply putting theta A dot equals to 1 in the set of equations for the velocities. Okay, so when codifying it, all we need is a subroutine where all the velocities are computed, and we pass theta A dot equal to 1 to the subroutine, and we get the Jacobians. Okay, next step is acceleration analysis. So we have alpha is the 0, 0, theta A double dot. So alpha is not known, theta A double dot is not known at any given step. So, and you have equations for the accelerations as shown in the slide. So again, just like velocities, accelerations also can be written in terms of the Jacobian and an additional component. So alpha A is j times theta A double dot, and acceleration of the point AO is JAO times theta A double dot plus the omega component. Okay, now the omega component of the acceleration can be computed by simply using theta A double dot in the equations. using theta A double dot equal to 0 in the equations. Okay. Now, using Newton-Euler equations, let us write the force balance and moment balance equations for body A. So these are the two: force balance, sum of the reaction force Fan plus the gravity force should be equal to the mass times acceleration, and which is nothing but the inertia force, and the moment balance is simply the torque plus R cross F equals to I alpha. Okay. So we have these two equations, and we also have from the acceleration analysis, we know alpha and A, acceleration of AO can be written in terms of the Jacobian. So we'll write that. So now we have three equations, two force balance and one moment balance equation. So all of these, the variables in red are the unknowns. So now if you write this in matrix form, we have in matrix form X equal to B, we get this. So everything in the matrix A and in the vector B are known. So this can be solved to obtain theta A double dot. Now this is using the Newton-Euler equations. Okay. Another method which is relatively easier is using Keynes equation, and Keynes method is based on principle of virtual powers, or Jordan's principle, which states that a constrained mechanical system performs motions such that the total virtual power of the constraint force and torque is 0. Okay. While using Keynes equation, you don't need to bring into picture the reaction forces. So the total virtual power is 0. Just like principle of virtual work, here we have virtual powers. So all the forces that are acting on the system are the torque and the gravity force over here, and then you have the inertia force minus mass times acceleration and the inertia torque minus I alpha. So now the total power of due to these forces and torques should be equal to 0. Okay. So this is your Keynes equation. So we know, we have written while doing the velocity analysis, we have seen that omegas can be written as J times A theta dot, JA times theta dot, and velocity also can be written as JAO times theta dot. Okay. So now this gives partial dou omega by dou theta is JA and dou V by dou theta is JAO. Using this in the Keynes equation, we get this, we get the equation below. Now again, using accelerations, right? We have also written acceleration in terms of the Jacobians and the omega component of acceleration. Okay. So now we have substituting these also. So we have everything in terms of Jacobians and everything else is known. Only the red quantities in red are the unknowns. So we can simply solve by solving this single scalar equation. So there is no 3 by 3 matrix multiplication in this case. So for 1 degree of freedom system, you get one equation. So this is how it is. We have already discussed how to solve an ordinary differential equation in one of the previous videos. So using the above equations, above methodology, and with the numerical solver, one should be able to solve the ordinary differential equation